I welcome Dr. Manu S Mohan to deliver the session. Thank you, sir.
Sir, sir.
Good morning, sir.
Good morning, sir. Good morning, sir. Yeah. Sir. Yeah.
Yeah, I think I have made you the co-host. You can share the screen. Yeah.
Yes. Yes. Is my screen audible, sir?
Yeah,
Is my
yeah.
screen audible?
It is visible and audible.
Yeah. Thank you. So I would like to introduce me first. Manu S Mohan. So
Manu S
I
Mohan. So
just one second. Some echo. Just one second. Some echo. Yeah. So is it audible, sir? Is it audible, sir? Hello. Hello.
Yes, sir. It is
Hello.
audible, but
Yeah.
there
Yeah.
is echo, it seems.
Sir, I don't know how to minimize the. Still, echo is there.
Yeah.
Sir, now it is okay.
It is okay.
Yeah. Okay, sir. So I was part. I was part of the academia for a long time. So rather than in the industry, so uh, I won't be talking much about the industrial standards that are followed in the metal testing industry. Um, so the first slide, we see the optical SEM and the DEM micrographs of the marriage industry. Still echo is there?
I think
No.
it's okay.
Sir, can you wait for 2 minutes? I will connect from another computer.
Oh, sir. Manu, sir, I think if you unmute the other system, you have two logins now. If you unmute the other one, I think it will be solved.
Hello.
Sir, the thing is, you have logged in two devices now. If you unmute one, I
Now it's clear, sir. Now it is clear.
yeah, now it's clear.
Yeah. Okay, sir. Okay. Okay. Thank you. Sir. Thank you. Yeah. So my talk will not be. Is my first slide visible now?
Yes.
So I will not be actually covering the industrial standards because I have been very for very less time only. I have been part of the metal testing industry. Most of the time I was in academia after my bachelor's and few almost close to 1 year I worked in a steel plant where I was not that much involved in the characterization, but yes, I have done so. I was more in the academia, so please bear with me if you think that I will be if you have thought that I'll be covering some industries standards and all. So the first slide I am showing before going to the somewhat advanced characterization techniques. First, we must see we must understand the scope of optical microscopy. So that is a very robust technique now also followed in industry, because industry the work the pace at which they work and they deliver the results are very fast, so they can't wait for a very long time. So CM, EBST, TM, all these things takes long time, so it is not feasible in most of the industries. So now also I have heard from one of the leading industrial experts who is working in EBST that he was telling me that industry is still not ready to do characterization in EBST or TM at a very rapid rate. They very specifically, for specific reasons only they use. For example, in Bharat Forge, where I was working for some time, they have their own center in Pune, KCTI, where they have the EBST. So very specific reasons only they do that. Steel, when I was there in steel making, where they were involved, most of the cases they were not using the EBSG. They were using optical and the CM. They were doing the character. They were carrying out the characterization. So here we see the first optical micrograph. The left side we see you can see some marks. So these are the basically metallurgists, they will know easily, or mechanical engineers. So these are the inclusions. So sulfide inclusion is very detrimental to steel because they generally have very low melting points. So when the steel is subjected to any rolling, forming, any other processes, so there is a very chance for the steel to crack. That is, the crack will originate nucleate at these inclusions. So these can be characterized by the optical microscope. There is no need for one to go to the optical microscope. Scanning electron microscopy or transmission transfer. In fact, very rarely when they want to ascertain the composition, they go for EDS. Otherwise, even they don't go for EDS. By morphology, one can check whether it is a sulfide or there is sulfide or alumina or oxide or silicate. So A type, B type, C type, D type, they say in the industry, all by morphology. That is L by D ratio. L by D, the L is the length of the inclusion and D is the width of the inclusion. You can see here the length and the width. So L by D, if it is greater than 2, less than 2, so based on that they classify. If it is circular, so they say it is, they call it, it is called the oxide inclusion. So all these are elongated because they are steel. When there's the sample also is collected in a specific manner. That is the axis of the axis along which the specimen is cut. That axis lies parallel to the rolling direction. So the rolling direction is actually matching the length of lies parallel to the length direction of this inclusion. So another thing is another thing what we have here is the microstructure of the carbon steel. So carbon steel microstructure, you can see them, the ferrite and the uh, basically the pearlite phase. So these are, ferrite means it's a BCC structure, and pearlite means it consists of alternate layers of ferrite and cementite. So that is why you can see here the dark and white lines here. And so somebody wants to, a metallurgist or any mechanical engineer, whether he wants to know his structure has whether it is low carbon, whether it is a medium carbon steel, or the hardness, he need not again just simply go for the scanning electron. So I'm not telling that he need not go at all, but first he should start with the optical microscopy. Then you have here the cast iron microstructure. Again, you can see here This is again they call it as it is not actually gray cast iron, but a variant of a gray cast iron, you can say. Some of the carbides are in the form of flakes, but some flakes you can see here more, it tends to be in the shape of some blocks. Okay, so whether how the carbon is distributed, some of the cast iron, the people are interested, because if it is a gray cast iron, generally it has poor fracture toughness. But whereas if it is more of in the blocky stretch, or if it is becomes a spheroidal graphite iron or vermicular iron, then the fracture toughness improves, because the graphite flakes are sharp. So again, they have poor fracture toughness, the faces, but they are having good vibration dampening ability. And then you see here the decarburization. Again, it's an optical micrograph. You see here uh, the gradation in color here. So when steels, where then they are subjected to very high temperatures, what happens? The carbon will diffuse, they will react with oxygen, and then the carbon dioxide or carbon monoxide, depending upon the temperature, it is released. So when what happens when carbon content decreases, there is a phase change happening here. So white color here represents the ferrite phase. So now industries are very much interested to know what is the depth of decarburization, because once it becomes ferrite, it is no longer it shows the bulk property similar to that of the bulk composition. The composition is not the same as the bulk composition. So what happens? You all know that metallurgy, the main thing is the property is dependent upon the microstructure. So again, these zones they are weak. So there can be these zones can cause again some failure or cracking. So next is a nitridation. So some of the industries, they are always interested to improve the surface properties. For example, you have gears. You have a gear core is actually very hard. Tough. It has good toughness. Toughness, I mean, better ductility. Whereas when it comes to the surface, it is more hard. So people, this is surface modification technique, nitridation. They expose the steel to nitrogen atmosphere. So nitrogen, it can be liquid, it can be solid, it can be gaseous. So you have actually white layer forming here. So some of the layers are brittle in nature, whereas some are harder. So they want to assess what is the extent of nitridation. So in that case also, they need not go for the the scanning electron microscopy. So that is the one of the scope of the optical microscopy. Now you have the PCB cross section. These days, PCB people are interested to find out the extent of the effectiveness of the solder. So they want to understand what extent the solder has been solder is effective in conducting offering a conductive path. So if there is a break in the solder, or if there is a delamination of the copper layer. So PCB basically consists, all of you know that, PCB basically consists of copper layer, it consists of dielectric, it consists of pre-preg, that is another solder mask, so many things are there. So there's basically an organic part is there and the metal part. So they want to assess the thickness, whether there's any erosion, delamination. So for that also optical. So the side you see here, basically the glass composite. Okay, and then you see the copper foil. So again, we think that we now need to go for a CM always. No, first we have to the optical micrograph gives a basically better understanding, the initial understanding. Then further it is required, we have to go to the CM. So now, what is the limiting condition of an optical microscope? So resolution is one thing. So resolution, it says that it is the smallest distance between two objects that can be distinguished by our eyes or lens, which if it is optical microscope, it is lens. So we know that our eye, we can resolve we can resolve clearly, easily 1 mm in scale any scale, if you take 1 mm, it can be easily resolved, but below that, it is little difficult. So people say that we can resolve. It is written in books also that 0.2 mm we can resolve it at a particular distance. But an optical microscopy, what is the resolution? So the formula here is D equal to K lambda by Na. So where K is a constant, Na is the numerical aperture that represents the light gathering ability of the microscope, and lambda is the wavelength of the light array, array. So if you put the blue light, the lowest one, 436 nanometer, red has the highest one with GR. So if you have Na numerical aperture, that's a product of the sin alpha and the refractive index. Okay, so that is 1.4. So glass 1.5 is the refractive index for glass, and alpha sin alpha is 7. Alpha is 70. So if you multiply, you get 1.4. And then if you substitute, you get 0.2 micron. So that is the limiting thing in an optical microscope, apart from depth of focus, magnification. So main problem with optical is 0.2 micron. So if you want to see something which is below 0.2 micron, definitely we have to go further for another characterization technique. So how can we improve resolution? Resolution can be improved if we reduce the lambda value. We can improve the resolution. So magnification of optical microscope is now I'm in third slide. So magnification of optical microscope is given by M objective into M eyepiece. So here we have in optical microscope, we have objective 10, 20, 50, 100 x, and eyepiece we have 10x. So maximum we can have is 1000x. Okay, so that limits whether it is a biological specimen or metallic specimens. There's a limit which we can resolve. So now comes the optical and SEM micrographs of nickel-based superalloy, so which is used in jet engines. So they are used in it's a turbine material. The turbine blade material is most of they use nickel-based superalloy because of the high strength at high temperatures and erosion resistance, corrosion. The superalloy has high resistance. Nickel is around 50%, more than 50, 53%. Plus they have carbide forming elements like titanium, chromium. So now this optical microscope will give me simply annealing twins. So I will come into twin characterization later. So it just gives me twins, but further to that, I am not able to gather any information. So to gather the information, what I have to go, I have to do the EDS, the energy dispersive spectroscopy, which clearly gives me what are the elements present in it. Okay, so these are annealing twins. So we will discuss about twins later. So what is so now comes to the scanning electron microscopy. So what are its scopes? What is its scope? It's basically we are able to do the imaging. Okay, we can see the images. Apart from that, we can determine the EDS, WDS, so energy dispersive spectroscopy, wavelength dispersive spectroscopy, then the WDS. So basically what happens here, you have the electron gun. So in electron gun, basically you have the filament. So the filament is generally it can be thermionic source or it can be a field emission source. So if it is a thermionic, we have generally tungsten and lanthanum hexaboride. So if it's a tungsten source, so the probe size cannot be reduced much. So the field emission source, lab 6, so it will be generating very fine probes, and therefore fine probe means better resolution. So now with the electron lens here, we don't have glass lens here like in optical microscope. So what we have is the electron lens. So all of you know this. These lenses are basically used to focus, diverge the beam. And then we have the detectors. The detectors basically are the secondary electron detector, BSE detector. So secondary electron detectors, we call that as Everhard Thornley detectors. So secondary electrons are those generated from the specimen, whereas BSE, backscattered electrons, another set of electrons that are, they are basically the electrons reflected, scattered by the surface. So these are the electrons coming in, the electrons basically impinging or irradiating the specimen from the electron, the filament, and they are scattered by the specimen. So this gives the contrast, and then you have the EDS and WDS. So energy dispersive spectroscopy is what? Energy dispersive spectroscopy, you find the specimens, basically the when the electron beam strikes the specimen, X-rays are generated, and this X-rays, we will be discussing a little bit about X-rays also. And these X-rays are actually, these X-rays, when they characteristic of the particular element, they strike the um, photodetector. So when they strike the photodetector, they produce the intensity, they produce the voltage which is proportional to the intensity of that element. And like that, you then you have the famous Castaing's equation, which says that the intensity is intensity of the specimen by intensity of the particular element by intensity of the element in the standard is proportional to the weight fraction of that particular element in the alloy times the ZAF. That is, ZAF means the atomic number absorption and fluorescence factor corrections. Okay, so this is the main. This is how the SEM EDS works. So now we come back to SEM. It is the most important thing is the X-ray. So sorry, SEM EDS. The everything works by through the EDS is calculated by after recording the intensity of the X-rays. So X-rays, how they are generated? So X-rays, you actually have a X-ray tube. This is so this X-ray tube, I'm referring to X-ray diffraction, not the SEM. So in SEM, the X-rays are generated from the specimen, whereas in X-ray diffraction equipment, so which is another characterization tool which is heavily extensively used. So X-rays are produced in the X-ray tube. So X-ray tube, you have basically the cathode and the anode. The anode here is the uh, anode here is the copper target. Sir, am I audible, sir? Hello.
Yes, it is audible for me, but someone was saying that the sound is low.
Okay, sir. I will rectify that. I will. Okay, sir. Yeah. So I hope now it is audible, sir. I have moved my mic closer to my
Yeah,
microphone closer to
now
my
it
mic.
is okay.
Yeah. Okay, sir. Thank you. So we have the X-ray tube. So in X-ray tube we have the target material, which is the anode, and we have the tungsten filament, which is the cathode. So what happens here? You apply several thousands of volt, 30 kV. So when you apply the voltage, what happens? The voltage is higher, voltage is high enough to uh, cause the electrons to be drawn out from the target. Sorry, from the tungsten electrode, they are drawn out from the cathode. That is, tungsten electron, the electrons from the tungsten, when they are under the heavy potential, they are drawn towards the positive terminal. Positive terminal here is the anode, that is a copper. So when the electrons strike the anode, that is copper material, there's a copper, pure copper. Uh, so when it strikes the copper, on the collision, the we can have two sorts of X-rays, basically the characteristic X-rays and the continuum X-rays. So that's what is plotted in the left side. Characteristic X-rays and plot there as a function of voltage. It is plotted here. So continuums X-ray, they are actually when the bombarding electrons decelerate, you produce the continuous X-ray. So which is you have a background here. Whereas when it strikes at a very high, whereas if you have characteristic radiation also, not only continuous X-ray and characteristic. So characteristic radiation, they are produced when you knock out an inner shell electron from an atom. So from the copper atom, so you can have copper, you can have molybdenum source. And so from other sources also, because still people, they are not interested in copper, many of them, because of the fluorescence. So they use molybdenum target. So from copper, you produce the characteristic X-rays. So these characteristic X-rays are, why they are called characteristic? Because they are characteristic to the target. For a specific element, there is a specific wavelength at which there's a specific wavelength for the characteristic waves. So you have the K alpha and K beta. So now here the K alpha 1, K alpha 2, they are for the moly target. Whereas for copper it is 1.54 angstroms. So you can see something like K alpha 1, K alpha 2, K beta 2. So I will discuss about that in the next slide. So yeah, so you have the next slide. I am going to the next slide. You have the Rigaku diffractometer. So generally, you have two types. Generally, in one is the sample is stationary and the specimen and the source moves. So that is one sort of detector. There is one sort of assembly. In certain cases, the detector will be stationary, whereas sample sources both will move. And in some of the mechanical engineers, they will be interested to understand study the residual stress. I have not, unfortunately, I couldn't cover it. In some other chance, I will try to cover that, given an opportunity. So you have the focusing circle. So the specimen is stationary here, whereas the detector and the source move. So whenever the detector moves by 2, whenever the specimen moves by theta, the detector moves by 2 theta. So basically you have the Bragg's law, lambda equal 2d sine theta. We'll come to that next slide. So that is followed. So whenever you have the reflection, lambda equal 2d sine theta is followed, you have a reflection. So now comes the emission and what is K alpha 1, what is K alpha 2. So suppose the K shell is the n equal to 1, L shell is n equal to 2, and n equal to 3 gives this M shell. So from K shell, if you knock out an electron, that is, you saw that in the copper target, when the electrons from the tungsten filament, when it strikes, your K base, if it is K shell, electron is removed, and from L3 subshell. Okay, so in L shell itself, there are 3 subshell. 1, 2, 3. So you know that 2s shell, in second shell, there can be 2s, 2p. Okay, so 2s and 2p are the 2 subshells in there. So from 2p subshell, if an electron, that is the third electron, comes and occupies the K shell, then what happens? Because if it's knocked out, so then you have a K alpha 1 X-ray being liberated. So similarly, if from L2 subshell, if the electron occupies the K shell, that it is called K alpha 2. So now you have the when in the X-ray pattern, when you have the K alpha 1 and K alpha 2, so you have this issue, that is, K alpha 2 will be very close. It's called a doublet, so it has to be stripped off. So most of you who do X-ray, they will, when the operator give you pattern, or when you practically do that, definitely you will be stripping off K2. So now I come to the X-ray plot. So you can see here the XRD plot of my alloy here. So it is captured at different temperatures. So we have here the room temperature. It is showing, it is a lot of peaks are there. So why the lot of peaks are there? Because it is a low symmetry phase. So it is a monoclinic phase. So whether when you have a cubic phase, you have very nice pattern, but unfortunately it is not cubic, so you don't have those fine peaks here. So now, so if you increase the temperature, what will happen at 180, close to 180 degrees Celsius, you still have peaks, but the moment you go to 300 degrees centigrade, many of the peaks disappear, because this is a shape memory material. So shape memory material means there is a transition from monoclinic to cubic phase at higher temperatures. So at higher temperatures, you see the peaks being disappearing. You see the disappearance of the peaks. So you will see here some silicon peaks. So what are those silicon peaks? Basically, those are the peaks from the holder. Okay, so since it's a high temperature, since these X-rays are captured at very high temperature, so what happens is specimen, there is a high chance for background to come. So background, since it's a high temperature stage, we use alumina. Normally we use glass, which is amorphous. Many of you who have done X-ray, you would have seen glass filament, but when you do for high temperature X-ray, you cannot keep in glass, you keep in alumina. So this alumina or silica. So what alumina? So to prevent the alumina peaks from appearing, we kept silicon. So that is why you see the silicon peaks. Now these peaks only you are seeing that. So now you see here the X-ray peak position. So many of the students who are doing, I suppose the audience is mainly faculty and researchers, but if at all some students, so they will be wondering what is the significance of theta and what is the significance of theta. So theta intensity. So theta is the theta. I will get a peak at theta when Bragg's law is satisfied. We will discuss about Bragg's law. So whereas I get a peak, so that is proportional to these factors. So whenever we see an intense peak, it is proportional to polarization factor, it is proportional to structure factor, multiplicity factor, Lorentz factor, absorption factor, temperature factor. So many things are there. It's not just the structure part alone. There are the factors which are apart from the structural detail. There are many other factors which contribute. That's what it says. So I have given an arrow here, so this shows interplanar spacing. So interplanar spacing means basically the spacing between the planes which is affected by allowing addition, so and so. So multiplicity factor, yes. Why multiplicity factor? Because in cubic crystals you have, I assume that many of you are very comfortable with what are Miller indices. Basically these are Miller indices 100 bar 10. That is, they are planes. So when you take a cube, the faces of the cube are basically a family of 100. So assuming that it is cubic structure, so 100, 010, those are the planes of the cube. But in cubic structure, you have 100, 010, and 001 all having the same d spacing. But the moment you go to higher crystal systems like tetragonal, monoclinic, trigonal, orthorhombic, they are no longer same. So there the multiplicity is less. So that is what I'm trying to say is, when your specimen has 100 or 010 or 001, you basically, all these can contribute to a peak. Same peak. It will not be multiple peaks. That is, if you see here in my, I go to the previous slide. If you see my cursor here, I have shown two planes, 011 and 10110. These two peaks are different in monoclinic because your A, B, C, the lattice parameters are different. Whereas in cubic, your 011 and 110 will not be different. They will be the same. You can mark it as either 011 or 110. It will be the same because the d spacing is same. So if you put the d spacing, if you calculate the d spacing for cubic structures, it will come as the same. So that factor is multiplicity. So that has to be taken into account in the intensity, in calculations. Therefore, P for is 100 is 6, 111 is 8, and it depends upon, as I said, it depends upon the crystal structure. So it is for tetragonal system, it is 4. Then you have Lorentz polarization factor. So Lorentz, so these are the Lorentz polarization factor contributes to, it is actually a product of it is due to the trigonometrical factors. That is, you have when it is theta is very small, you have many planes which are closer to the Bragg angle. Okay, and when you have and the diffraction cone, actually we think that it is two-dimensional, but basically you can have a three-dimensional cone being produced. So this cone has also the intersection of the diffraction cone is higher when it is a lower angle. So that can be imagined easily. So then you have the Lorentz polarization factor. So taking all this polarization, it is also there is a Lorentz factor. Polarization factor separately. That polarization factor is arising because your incident X-ray beam is unpolarized. Because you know that X-ray is an electromagnetic electromagnetic wave. So you have the electric field oscillating perpendicular to the path in the direction, perpendicular direction, so that it is unpolarized. So that also takes part. So that also affects the intensity. So the we can resolve the vector, the electrical vector, and find out how much what is its influence on the intensity. So Lorentz polarization factor, if you take all these factors, it is 1 plus cos square 2 theta by sin square theta into cos theta. Basically, what I want to say is this: it is dependent upon the Bragg angle. Dependent upon the Bragg angle, you will have an intensity which is quite different from what the contribution of the structure. So then you have absorption factor. So it is equal to 1 by 2 mu. Mu is the absorption coefficient, because you have the sample, when you pass the X-rays, some of them are being absorbed by the specimen. Some of them pass the electrons, pass the X-rays, it is not completely diffracted. Some of them are being absorbed also. It is 1 by 2 mu. It is not dependent on theta, because whether you have a smaller angle or a larger angle, the volume that is irradiated is the same. Then you have the temperature factor. So what is temperature factor? So temperature factor, because as you increase the temperature, the periodicity is slowly getting degraded. So whenever you say X-ray pattern, you talk about the X-ray pattern at the room temperature. Generally, not room temperature. It is at room temperature you have a periodicity, but when you heat it, the periodicity is affected, because the lattice atoms vibrate about its mean position. So that will affect the intensity. So therefore, you have e power minus 2m, that is the empirical, that is estimated factor. So that has to be multiplied. This m is proportional to the Debye factor, is proportional to temperature, so many things. So finally, the structure factor, FHKL, is, that is the structural contribution, is something, it's a critical part. So many of us tend to ignore that factor, even in many among the research field also. When they are young to this, when they are very in the big early stages, people tend to ignore this, those who work in the materials. So it is actually, the structure factor can only be understood properly. Even I feel now also very difficult. Many, if you deeply understand the crystallography part, then only the structure factor can be easily understood. So the structure factor is the product of basically you have the phase difference factor between two electron waves, two X-rays, that is being taken into consideration by e power 2 pi I into hx plus ky plus Lz. That is, the phase difference part is taken care by that factor, and times the atomic scattering factor. The atomic scattering factor is nothing but the ratio of the amplitude of the wave scattered by all the atoms in the unit cell by the amplitude of the wave scattered by one electron. So now if you take all these factors, you basically get F square P. So where F is intensity is a product of structure factor. So basically your F square means only the amplitude you are considering here. So mod of F square, mod of the structure factor, modulus of structure factor times the multiplicity times the Lorentz polarization factor times the absorption factor. So now I'm showing you why you need to know the structure factor very clearly. You see here the two structures I have shown here in the right side. One is pure iron and one is NITI. Both appears to be body-centered cubic. We will say like that. It is body-centered cubic, but it is wrong. It is both are not body-centered cubic. Body-centered cubic, you only say that when all the atoms are same. For example, in the first one, it is the left part is simulated this XRD pattern. This is simulated by Foolproof. Foolproof software is freely available in the internet. It spells as FULL PROF. I think some of you are already aware of it because it's freely available. People publish results using this software also. So if you see here, it's a simulated. It's easy to simulate the diffraction pattern here in pattern. So if you see here the pure iron, you see all are dark. So you see here all the atoms at the corner and atoms at the center, both are iron. Okay, so you have when you substitute in this expression, f is equal to capital F is equal to small f into exponential 2 pi I into hx plus ky plus Lz. You substitute that, you get f is equal to 2fe when h plus k plus L is even, and f is equal to 0 when h plus k plus L is odd. So I come back to that expression again. So here h, k and L, f is equal to f into exponential 2 pi I into h plus k plus L. H, k, L basically represent the Miller indices of the plates. Whereas U, V and W represent denote the coordinates of the atoms. So you have two coordinates now in body-centered cubic. In body-centered cubic, there are two coordinates. One is this particular atom is showing 0, 0, 0, and the center atom, the coordinate is half, half, half. That is, if I move by x by half and y by half and z by half, I get into this position. So these two coordinates, if you substitute, then you can get, and e power 2 pi I, and if you expand it, you get the expression, and then you get two conditions. That is f equal to 2fi, 2fe when h plus k plus L is even, f equal to 0 when h plus k plus L is odd. So what is the significance in the pattern now? If you see the pattern, you see here 110 marked here, 200 marked here, 211 marked here, 220, 310. All these peaks, if you see here, in none of them you will see you will see the plane in which h plus k plus L is odd. For example, 110, if you add 1 and 1, it is 2. So again, so f equal to 2fe. So then f equal to 2fe means you get as per this expression, I equal to f square into p into Lorentz factor into absorption, you get the pattern. Whereas, I'm sorry, I have not substituted put the temperature factor there. Please bear with me. Temperature factor will also be there here. I have not put it. The actual temperature should come. So then if you put f plus k plus L, 200, 211, 220, 310, 322, in all these peaks, you don't see any plane in which the h plus k plus L is odd. Even 222 all are even. Okay, so therefore you don't get any peaks there. Clear? So now when we go, I think it's clear. So when now you go to NATA, it appears to be again body-centered cubic, but there lies the point. It is not body-centered cubic. It is called simple cubic. You see here the corner atoms are nickel, whereas the body-centered atom is titanium. So if you substitute again, if you substitute 0.5, 0.5 and 0, 0, 0 in the expression for f, you get f equal to fni plus fti when h plus k plus L is even, and f equal to fni minus fti when h plus k plus L is odd. That is, it is no longer it is not body centered cubic, but it is simple cubic. So you get all the peaks. You will see 100 here. You will see, so 1 plus 0 plus 0 is 1. Again, it is odd. Similarly, 210, it is odd. So not only for even reflections, for odd also you see that. So that is the difference. So one, if you want to what if one wants to interpret XRD, they have to. It's not that we use some very high instruments and get very scientifically advanced instruments, but it's also very difficult to analyze, interpret structures. So these are just the basics. Further, you have to do ritual refinement. So many things have to be done to characterize properly what is in the material. Okay, so now these are the, so one must know that what are the Bravais lattices, okay, and what are the crystal systems, and where you're, whether if you're taking a lead oxide powder or any powder, you are working on aluminum composites, something, and you get some phases. We first know, we have to know in which of this it falls, whether it is monoclinic, whether it is orthorhombic, whether it is rhombohedral. Then based on that, we have to find out, search in the literature, or you have to look at the or you have to simulate pattern by flow to get the X-ray pattern. Okay, so now we come, sir. Now it is audible, sir. Hello.
Yes,
Am I
sir, it
audible,
is
sir?
audible.
Yeah. Okay.
Yes,
Thank you.
yes.
So yeah. So now we slowly move to the TM part. So we have a TM, and so now we have briefly covered what is, how optical works, how CM works, how X-ray works, and now we are going to the TM part, which is very advanced. And I believe in Kerala there are only one or two institutions, I think. Um, ISER Thiruvananthapuram, and then we have in, I think, NIST Trivandrum and ISER Trivandrum are the only institutions. I think they have, maybe NIT Calicut. The problem is, the main disadvantage is, the limiting factor is, it is in crores. So it is in 11 to 12 crores when I was operating in Bangalore. So it was, while I was a student, I used to operate. So it is 11 to 12 crores, and operation, getting results, everything, it's very costly. So you cannot, many of them can't bear. Many of the researchers here, unless they have they have got some projects, or it is very difficult to from their supervisors, or if they are not they are able to invest, it's very difficult. So I think IAC Bangalore charges close to 2.5k, 2500 per hour or so, if I am right. So that is the major issue with the TM. So here, even though you can see the two figures in the left side, you see the uh, SEM image. So here mm, you have a high depth of focus. That is, it gives a 3D picture. It has along the z-axis, you can see the gradient in the contrast. Whereas this TM, you don't have that. It is more like a 2D image, but resolution is improved. So this is the classic classic photograph of a TM. You have the uh, gun here. Field FEG is the field emission gun here, and you have the condenser aperture here, and you have the specimen holder here. The specimen is loaded here in the diagram, and then you have the aperture, objective aperture, slightly placed above the specimen there. The objective aperture, the objective lens is the heart of any microscope, whether it is there is optical, TM, CM, all this, the objective is the heart. So now, and then you have the camera here. So the operator, as you know, so they are the one they see here through here, these lenses. So now, so now the as in optical microscope, if you remember, the function of the condenser lens is to focus. In optical microscope, the function of the condenser lens is to focus the light beam on the specimen. So similarly in TM, the condenser lens here also it is like focusing the beam. In objective, in optical microscope, what is the function of the objective lens? So there the objective lens function is to form the first image in its back focal plane, which will be magnified by the eyepiece. Similarly here in transmission electron microscope, you have the objective lens that actually forms the it can form both it forms the image as well as the diffraction pattern in the back. It forms the diffraction pattern in the back focal plane, and it forms the image in the image plane, and that will be magnified by the different lenses. So now I come to the preparation. So the TM preparation, like optical and SEM, as you know, it is preparation takes hardly maximum few hours. So in industry, they prepare optical by maximum cutting, polishing, everything. They take hardly if they are if they are very fast, they may prepare everything by within 10 to 15 minutes. An optical microscope specimen, the specimen can be made ready for optical. Similarly for SEM, you have to be a little fine polishing has to be done. So maximum half an hour to 45 minutes, the CM can be Swiss oil can be prepared. Whereas TM, it cannot be. It is not like that. However skilled you are, it may need more than it may need almost half a day or more than that. Sometimes almost one day. The reason is that if you are hasty or if you are very quick, then what happens? You will deliberately induce artifacts. There is a tendency, there is a higher chance for the dislocations or any other defects to be introduced in the specimen. So it has to be carried out very slowly. The specimen has to be prepared. So at least from once it is, so first thing is to make a 3 mm disc. So I hope that many of the mechanical engineers here, they are all from the sorry, they are working on the steels or high-end alloys. So for them, it will be for even for if there are from chemistry background, for them also 3 mm disc, 3 mm the TM the for chemical engineers and the chemists or physicists, they will be interested, if they are interested to see nanoparticles, they will be dispersing on copper grade. So whereas in metallurgists or mechanical engineers, so they will be more interested to make a 3 mm disc first. So 3 mm disc can be made by wire EDM, or punch is there, mechanical punch is there, I have not put. So once you get this specimen, you have to polish it. So whatever be the initial thickness, so initially when I was doing TM, I used to section it to close to 600 microns or 800 microns, because if you try to section it below that, around 400, 300, it is possible by the use of very good low speed saw blades. Basically you can get it, but the chance for the specimen to be bent is very high. So in such cases, if you take the TM, there will lot of artifacts will be seen. So these artifacts appear as bent contours. So when you try to publish it in good journals, they may ask, it may not be rejected, but what are all those questions you have to answer, you have to justify that. So here the specimen is polished from 300 microns, and they are polished to close to almost 100 microns. The specimen is polished. Then that specimen is taken to a dimpler. A dimpler means it will be a wheel will be revolving on the rotating above the specimen. So you make a hole that you have to be carefully. You have to carefully see that, because if the depth is reduced much, then you will not get the electron transparent region. The purpose is to produce an electron transparent region through which basically the electron beam will be going through. So that is very important. So in transmission electron microscope, as the name says, the electron beam will be transmitted through the specimen. That is one of the important criteria. So your specimen is to be made electron transparent. So when you try to make it TM foil for the young researchers, I suggest that they don't take 1 or 2 specimens, take at least 3 or 4. PSG College of Technology has advanced characterization facility, so they have the preparation setup, and it will be at a subsidized rate. They will be charging at a subsidized rate compared to any other places like IITs or IAC. PSG College of Technology will be doing it at a very lower price. So then, you have to thin it down, and once you thin it down, once you dimple it, then you have to take it to either a precision ion polishing system or a electro polishing unit. This is called a precision ion polishing. So precision ion polishing means you subject the specimen to you expose the specimen to gallium ions. So gallium ions will be continuously bombarding. So you can see here the pips. So here there are 2 guns here. So these guns, you have to adjust the angle and you have to adjust the power. So this gallium ions will be striking that's what ion beam shows here, from bottom or top, and then you have a very thin region being developed. So, and you can produce a hole here. So now the hole is called in TM we call it as vacuum. So adjacent to hole you have the electron beam. So if you can afford more specimens, and if you're very much interested to get much larger area, you go for electropolishing. So electropolishing, your sample acts as the anode. Typical electropolishing in any electrochemical reaction, your sample acts as the anode, and there will be, I think, a platinum electrode, and which will be dipped in an electrolyte, and then when you apply a potential, the reaction happens, the anode gets oxidized, and you produce the hole. So this hole acts as the electron transparent region. Okay, so now comes to TM. We have to see what is the TM. Actually, we can the first slide, if you remember, I have shown some diffraction pattern. So it has both the imaging mode as well as the diffraction mode. So imaging mode is nothing. You have the right side is the imaging mode. You remove the selected area diffraction aperture, so you see the specimen. So in this ray diagram, it starts from the specimen. All the top things like condenser lens, the objective, there are 2 lenses, the upper pole and north pole, the upper pole piece and the lower pole piece. Here only the lower pole piece is shown here. So you can see the objective lens here. See, this objective lens actually focuses the specimen. So whichever planes in XRD, when you get the XRD, if you remember my XRD slide, I told that the 2 theta, whatever you get, is it is where you get the peaks is function of the interplanar spacing. Whenever lambda Bragg's law is satisfied, you get a peak. That is lambda equal to 2d sine theta. My left side is lambda always, it's a constant. So right side is 2 into d into sine theta. Again, 2 is a constant. So d into sine theta. So when my d changes, sine theta will change. So that is the basically the essence of Bragg's law. So here also you have Bragg's law is obeyed here. So whenever the crystals are at Bragg's law is satisfied, you get a reflection here. So that reflected rays you can see in the right side. So as well as the left side. So right side, the reflected rays are actually forming an image at the image plane. And this image, the right side, this image is magnified by the intermediate lens. Now comes to the diffraction mode. So how the diffraction mode works? You have to change the strength of the imaging lens. So you know that the lenses in optical are made of glass lenses, whereas in electron TEM as well as in SEM, they are electron lens. Why they are called electron lens? Because they use the current that is passing through the lenses to produce a magnetic field, and that magnetic field will interact with the electron beam. So it will try to focus, diverge, everything. We use these are electron lenses. Basically, they are electron lenses, but they appear here as like a glass lens. So now you change the strength. You actually you reduce the strength. The spots you see here, that's three spots will be further away from the specimen, and then that three spots you are focusing, that is the diffraction pattern. So basically, an imaging mode and diffraction mode, you can switch from easily with ease in while you're operating a TEM by just changing the strength of the intermediate length. That is, I adjust the current through the intermediate lens. You can change the strength of the lenses, which will decide whether you want to focus a final image or whether you want to focus a diffraction pattern. So now you see here the nickel based superalloy, the superalloy which you saw earlier. So there are three modes here. So you have the dark field, bright field. So you see that you can vary the contrast. Okay, so you see here again the bright beam and the diffracted beam. So if you try to focus only the bright beam and use it for analysis, whether if it is for imaging, you are only using the direct beam. That is a beam which is coming, which is incident of the specimen and which is not diffracted, that is, which is transmitted through the beam. You produce the direct beam bright field image. Whereas if you use the diffracted beam to form the image, then you call the dark field. So you can correlate one to one. So if you are using, because you see some white features in this, contrast is enhanced, you see some white features in dark field, because these are the features which have diffracted the direct beam. That is why that is appearing bright, whereas those appear darker in the bright field. So you can also, you need not tilt the beam always. Instead, you can you need not there is a provision for you to tilt the beam also. Okay, so that is then you bring it to the center, so you get the center dark field images. That option is also there, and you get the diffraction pattern also. So electron diffraction pattern, why they are used? For example, you have some you are into R&D, pure R&D in your metal, and you have some nanoprecipitates. You do some imaging. If you do some heat treatment, for example, aluminum alloy, you do some aging. You generally in mechanical engineers, since I was there in PhD for a long time, so they were many of the PhD mechanical faculty, they work in metals and alloys. So they will be doing some studies on the aged composites. Okay, so these and they will be mostly into the FEA part, finite element. They will be doing the machinability studies. And some part they may use metallurgy. So aging, what is aging is something which I'm trying to show some light here. So aging means you are producing some nanoprecipitates. So that nanoprecipitates you cannot see by optical or SE. So that we have to go for TM. So again, this is part of your studies, means it's important. But whereas if you're more into the design part or the machinability or the machining part, may not be very much required, but those of you are interested, it will be required. So if you want to see what is the precipitate, what is its orientation, how it is appearing, definitely you have to go TM. So identity of phases and their orientation relationship to the matrix, habit plane. So habit plane, again, it's a material science term. So that is those planes which are undistorted and unrotated. So those are called the habit planes. Then you have the if you have some, for example, you are using a radio a material steel which which will be put in nuclear reactors. So definitely you have radiation induced defects. Any defects are there, any vacancies there. So any Frankel defect, sorry, any radiation induced defects. So that time you have to go for again the TM. And order disorder transformation, spinodal decomposition, magnetic domains, all those things are also, they require TM. So now we go slightly deeper into TM. So here we have it all originated from the basic um, Young's double slit experiment, I think the theory. So when you pass a light radiation through a slits, you get basically the alternate bright and white layer. So these are slits. So many of the exhibitions you see students doing this. They produce the slit, the bright maxima, which is surrounded by, encircled by the um, dark lines. So alternate dark bright lines you get there, and then these dark bright lines are they are for the slits. It is okay, but fine. But in the crystals you don't have the slits, but you have the atoms. Okay, so when atoms are there, it's this slit. You replace in your mind. Replace slits with the atoms. So then what you get in the screen, basically you get, instead of the dark bright contrast lines, you get basically the reciprocal lattice. So reciprocal lattice is something which it's very common in X-ray as well as the TEM part. So you have the incident beam here. So whenever the LHS is equal to the RHS, you get the reflection. There is lambda is constant here. As I said, X-ray, the copper K alpha is 1.4 angstroms. So the only variable term here is DHKL and sine theta. So sine theta is also fixed when you fix it for an angle, particularly in X-ray source. The X-ray incident angle at a particular incident angle, sine theta is fixed. So that day, so those planes will satisfy this equation, those planes will give a reflection, whose interplanar spacing will satisfy this equation. So when you fix it sine theta, when you fix lambda, okay, you have some crystal, some plane which will have a particular D which will satisfy this equation. So assume that those are these planes. So you get a reflection here, and you can physicists normally assign the incident radiation as P0 by lambda. So which is actually the wave vector, and P by lambda is the scattered vector. So now I'm not going to all of this, but just want to say that whenever that P by lambda, whenever your so P by lambda is the path difference. So whenever the basic how is Bragg's law derived? So basically you find you find out the path difference. So path difference is there actually 2D sine theta. So if you draw a crystal and then if you mark it everything D spacing and say that when the phase difference is 2 pi or when the path difference is lambda, you get a reflection. So that is how. So here also we have that P by lambda is the path difference between the two rays. So if you take the 2D P by lambda should be, and the P by H or P by lambda, it should be a integral multiple of this wavelength. Then only you get the reflection. So the P by lambda people have equated to HA star plus KB star plus LC star, where A star, B star, C star are the reciprocal lattice vectors. So and these reciprocal lattice vectors have a relation A dot A star equal to 1. That is because only if that condition is satisfied, the P by lambda you can satisfy this equation. That is, if P by lambda is equal to A star, then A star to S. So if you multiply that, then only the right hand side will be satisfied. Right hand side of the equation will be equal to the left hand side, then only the equation will be consistent. So therefore you have the reciprocal lattice and the regular lattice, real lattice, bearing a unique relation. For example, two important properties are there. So that is, I have not covered the derivation here, which will lengthen my talk. So I thought not to do that. So there are two important properties here. One has to observe it. That is reciprocal lattice vector. That is GHKL is normal to the plain HKL. So GHKL is a normal to HKL, and the magnitude of the GHKL, that is reciprocal lattice vector, again, it's 1 by d spacing. So I show here, in the next slide, you have a real lattice here. So here it is showing here 100 plane, 010, 101, 001 plane. This is a real lattice, and you see here for each of these planes, basically you have a reciprocal lattice. That is, reciprocal lattice actually, it's an imaginary lattice or a mathematical concept where it is actually a Fourier transform. It's a Fourier transform of real lattice, basically gives you the reciprocal lattice. Okay, so that is like in your time domain is transformed to a frequency domain. So similar analogy is there here also. You have atoms here, so you have a family of planes being represented as a single plane. Family of planes are denoted as a single point here. So you see here 010, that is a reciprocal lattice point. That is actually a representative of 010 planes in the real lattice. Similarly, 101 plane reciprocal lattice point is representative. It represents the family of planes in the real lattice. Okay, so now then comes the railroad. So that is slightly advanced concept. So railroad, we are trying to say, because these roads are, the TM disk actually is thin, very thin in nature. So even if you don't you don't satisfy the your all the reflections don't satisfy the Bragg's law, you can have few reflections at the near Bragg angles, basically because the destructive interference is not complete. Okay, so that's what is written here. So because of the incomplete the destructive interference, incomplete destructive interference, in the direction, okay, and near the exact Bragg angles can also give a reflection. Okay, so now we come again to the most important point, the Ewald sphere. So Ewald sphere, it's very important to understand the next characterization I am discussing, with which I will close it. So you have the Ewald sphere here. So Ewald sphere has a radius 1 by lambda. So you mark the origin of the reciprocal lattice, and if you plot it, wherever the reciprocal lattice, the Ewald sphere strikes, that particular reciprocal lattice will give the reflection. So that is why, how we can derive it. So Bragg's law can again be derived from this concept. So if you take OB, so in this is how to draw the Ewald sphere is something which is very interesting. So even very difficult for me to understand now also. So but I got a small glimpse of that. So 1 by lambda is the radius. 1 by lambda is the radius of the Ewald sphere. With that, if you draw a sphere with O as the origin of the reciprocal lattice, then 1 by lambda, this is the radius of 1 by lambda. This is the incident vector, and this is, suppose this is the diffracted vector AB. So then that will also have a same magnitude. Why it has same magnitude? Because it's an elastic scattering. So energy is conserved, so you have the same magnitude. So now you can have a geometrical construction here. You extend it. So if you take OB by 2, you can write using the angle in a semicircle is 90 degree. So OB by 2 is 1 by lambda sine theta. So if you expand it, lambda equal to 2d sine theta. So Bragg's law is proved from Ewald sphere also. So that means OB will. So since Bragg's law, you are able to derive, assuming that OB B is a point or a reciprocal lattice point that gives reflection, OB vector satisfies the Bragg's law. So therefore, wherever eval sphere is cutting through the reciprocal lattice, you get the sphere. So that's what drawn here. So now in the next slide, I have the reciprocal lattice and the eval sphere being drawn. So wherever the eval sphere is intersecting, you get basically the sphere, the pattern. So now you have this is a railroad. So you will see the reciprocal lattice. It is not just 0 and 4G, where it is proper 0 and near to 3G and 4G, some point is there. So GHKL, I told, that is what is GHKL? 1 by DHKL. It is inverse of wavelength. So now some of you who have taken diffraction patterns, for them to index it, if you have a doubt in indexing, if it is a cubic crystal, you can please refer to this book, Eddington, Practical Electron Microscopy. It can be downloaded from, it can be, since the copyright issues, other things are there, I don't want to tell the sources, but you can, you know how to download. So you can download. So there are other patterns. So simulation of TEM, simulated SAD, selected area diffraction pattern. So you can generate a TEM diffraction patterns using, these are the inputs: lattice parameters, space group, atom coordinates. With all this information, you can generate so only if you have all these three. The lattice parameters, first you need to know, if I want to know what is the lattice parameter. So a diffraction pattern means reciprocal lattice. Okay, so I'll come to that slide, next slide, and make it clear. So you have to have the knowledge, you need to have the knowledge of three, basically: the lattice parameters, the space group, and the atomic coordinates. Only when you have all these three, you can have you can produce the diffraction pattern. Again, this is from my thesis work. So this is a TM bright field micrograph shown here, and then you have a diffraction pattern. So diffraction pattern, as I said, each spot, what it basically represents, it represents to me a reciprocal lattice. So that is, I have written something like 101 here. I have written bar 2, 1, bar 1, 2, 1 here, and 1, 1, 2. So all these basically represents a family of planes in the real lattice. So what we are getting here is a reciprocal lattice. Basically, through lenses, you are able to you focus the planes coming through, you are able to focus the we are able to focus the beam intensity to a point. By the use of objective lens, you are able to focus the intensity of the beam being scattered by a family of planes to a particular point. That is what is shown here. So these are basically the points. Each of these points basically represent the reciprocal lattice. Or in the real lattice, if you want to imagine, you have to imagine that they are the intensity from a set of planes which satisfy the Bragg's law. So this basically forms the Weiss's-Sohn law. I don't want to go to that, it will take time. So it's a particular, when electron beam is parallel to a certain direction, it obeys a certain law called Weiss-Sohn law. From that you get this. So now two things you observe here. One is, this is 0.2 microns. So each of this parallel, you see here some of the lines here in the, so these are twins actually, their spacing is 5 nanometers. You imagine 5 nanometers. So something like 50 5 nanometers, you can have around 50 angstroms if I'm right. Okay, so the that many, so around close to, you can keep around one aluminum unit cell itself is 4 angstrom. So 4 angstrom, around 40 aluminum such cells can be kept in this. So you are able to deduce much information from this TM micrograph only if you are very particular to, you are able to get the information, and you have to go to the scale only if that relevant information is very relevant. So some of you might think, why I have taken this image. The reason is that this type of twins influence my mechanical properties, which the mechanical engineer is interested. Mechanical engineer, his perspective will be how much strength I will be getting, how much ductility I will be getting, how good the fracture toughness will be at this particular temperature, how much I will get, so that he can put in some of the calculations and know that whether material will withstand this much load. But a metallurgist, on the contrary, uh, might be much more interested, might be interested whether my nature of twinning will contribute to this strength. For example, why I have gone is this twin, this space, this type of twins will influence the mechanical properties. For example, I need 2% of shape recovery, 2% strain, complete recovery. Whether I can, whether if I have this twin, then I will get this recovery or not. That is my question. So I was worried about that. So therefore I have taken that. So then I, when I got this diffraction pattern, I actually simulated. So this is the before simulating the, before showing the diffraction pattern, you can see here twins. So these are the crystals. When you deform it, you can deform either by slip or by twinning. So twinning, some factor you have already studied in your uh, days, you have studied in your college or in your earlier part of education you have studied. So twinning, one part of crystal is sheared to other. So this is what you are seeing. This is a twin and the crystal, and you are able to see the twin close to 5 nanometer scale. You are able to see that these twins. Okay, so therefore we have gone for that. We have simulated the pattern. So the left side you see the simulated pattern, and right side you see the image, and we measured the angle. So just indexing, this is not very complicated, very easy job only, but you have to verify whether you have to simulate the pattern by 3 parameters. One I told, it is the lattice parameter, the other is the space group, and the other is the coordinates, attempt coordinates. You have to simulate it, you have to measure the coordinates. Then finally, you have, this is the tuning spot, the diffraction pattern, the simulated TM diffraction pattern, which I overlapped and matched it. So now you have to see. So in X-ray, how you match it? You see, you generate the pattern. Simulated, you have a simulated pattern or joint committee of powder diffraction standard files. You compare the peak position with the intensity. You may not match because it's in metals. It's very difficult to match because of the texture. When you roll it, when you forge it, when you subject to many metal forming operations, intensity will change. You cannot compare it. It's not easy. It has advanced softwares are required. So, but definitely you will match the 2 theta. Only if you confirm the 2 theta of experimental and they are matching, then you will say. So it will not match most of the cases. The other reason is the files are not there. Many of the joint committee of powder JCPDS files you will not obtain for alloys, because they are only for, many of them are only for pure metals, iron, copper, that. But some here and there, some alloys you will get, but many of the topics which you are researching you may not get. So you have to simulate it using advanced softwares like full prof, all those. So similarly TM, we have to generate, we have to see the spacing G101, it is 4.211. So you can see here it is in I will go back to the pattern again. You see here the x-axis 1 by nanometer. So it is reciprocal lattice. I said each G is equal to 1 by D. G is equal to 1 by D. Therefore, you have to it is a reciprocal. That is why you have to take the inverse of that. Okay, so also you have seen it as the p by lambda in the scattering vector, the magnitude is 1 by lambda. Okay, so now now I go back to the pattern. So you see here they are matching exactly, but some difference is there. For example, you have angle G1 or G3. When I am trying to match it, I am getting 107, but here it is 109. So that is because of lattice parameter variation, which we cannot avoid. So we have to, the theoretical pattern also, we have to match it exactly. We have to find out the right source, get it done, all those things. It takes time, some time, but it is easy job. So next I go to the final part of my this is there in a few facilities in India, South India. It is there in IIC Bangalore. It is there in IGCAR Kalpagam. So Professor Arup Das Gupta is working on this. So they have this. So what is precision electron diffraction? So precision electron diffraction, you are basically you are overlapping the Wald sphere. Okay, so you basically have an electron beam which you spin it about its axis, which you cause it to revolve around its axis, and therefore what changes basically my Ewald sphere will change. So I said that Ewald sphere is an imaginary construction, just like our mathematical what is it reciprocal lattice. It's also imaginary sphere, which is actually it says that wherever my Bragg's law is satisfied, I get a reflection. So the TM based on this theory, these researchers have developed a technique called precision electron diffraction. So this came in Bangalore where I was working. It came in 2012 or 13 if I remember. So definitely it was discovered much earlier. So early 2000s or before that it was discovered. So sorry, it was invented, this one. So now then you can see here, when you have you have multiple Ewald sphere, that is revolving Ewald sphere, more spots come into more spots can be recorded or acquired. So each of these spots basically they correspond to reciprocal lattice, or they are basically vectors, or they are basically from the family of planes. So now this is what they do here. They take a crystal. Okay, so again, why you have to do? So normally, when I was speaking to your professor, Manu sir, so he was telling about EBST facility which he utilized for his PhD. So EBST, when it is actually used only, it can utilize if you want to find out the orientation up to the scale of few nanometers, like 50 nanometers or so, easily you can. But let's say you have features which are as close as 5 nanometer, which chemists or the metallurgists they are doing. Some of them will be few nanometers. So you cannot get the information at such a scale, even strains, magnetic domain. So you have to go with either TM or PED. So here it is like a more of a. I would we all so we can I used to say to my friends that it's more like a TM based EBST. So they also produce the orientation map. So how it does is, so you have the electron beam, you spin it around the axis, you basically cause the Ewald sphere to revolve around its axis. Therefore, you get more pattern. Kinematic diffraction is satisfied. You are able to record much higher number of reciprocal lattice points. And then before going to my result, I want to say a few things about one or two points about how the texture is represented, orientation is represented. So this is the equipment. So you get an orientation map. Basically, you have a specimen. You tilt the electron beam using the beam deflection coils, and then using image deflection coils again you align the beam along at the center of the diffraction pattern. Then that pattern is compared with the uh, already stored simulated pattern. Basically in EBST, some of you have already done EBST, so you are aware that how the pattern is obtained. You compare with the already generated Kikuchi patterns. Kikuchi patterns are there, which will be compared with the acquired Kikuchi patterns, and then you give if the Kikuchi patterns are matching, you give a color code. Okay, and these Kikuchi patterns are generated using CIF files. CIF files are also same. They have the atomic coordinates, the space group, and the lattice parameter information. So all of them, these files have CIF files have. Here also here, instead of CIF file, instead of Kikuchi pattern, diffraction pattern from each point is captured using a camera. Okay, using a camera, that you can see a camera here. A camera acquires each of this diffracted beam as the beam rasters the specimen. That is, beam as the beam scans each point in the specimen, you record the diffraction pattern using a camera, and each point is compared with the theoretical pattern. Suppose you are doing on iron, you already have given them the material is iron, so these are my lattice parameters, these are the simulated, these are the atomic coordinates, all those things you load it free of cost from various websites. That then system will simulate those patterns and compare those patterns with compare it with their experimentally acquired diffraction patterns. That is what here it is done. So that is the way, and then they will give a color code, orientation mapping, all those things. Okay, so now basically a crystal has so many grains. So what are these grains here? Grains are nothing but crystals having unique orientation. So unique orientation, each grain has unique orientations. So you have the normal vector, you have the rolling, you have the rolling direction. So rolling, all of the mechanical engineers are familiar with the rolling process. It's a core manufacturing process. We have the we have in many of the steel mills. Also, you have the some of the steel plants in India, sorry, in Kerala also are doing that. So you have the rolling operation being done. So definitely, so you are aware of this. So you have the grains having a unique orientation. So you can see these are the unit cells. Okay, so each cell has a particular orientation. So grain means a unique orientation. Now, how you construct a stereographic projection? So these are important for understanding the TM PUD data. So you keep that at the center of the unit cell, center of the sphere. So this sphere, and then you plot the different, you plot normals to those planes. Okay, so 001 plane, you plot it towards, you project the pole normal from the plane to the reference sphere. So you have the 001, 010 and 01, so all planes, you can plot the normals to that, normals towards the northern hemisphere, and then draw a line from the southern hemisphere to the point of intersection of the normal on the northern hemisphere. So when you draw a line connecting the southern tip of the southern hemisphere to the point of intersection of the normal on the reference sphere in the northern hemisphere, you intersect at a point. So that line, when it intersects the projection plane, you get the two-dimension, you get the 2D version of the plots. Basically, that is called the stereographic projection. So you get basically the position of the poles on a 2D plane. So a 3D data, basically you are transforming, you are plotting the 3D. You are getting the information from the 3D space, you are plotting it on a 2D space. Okay, so like that you can plot all these poles, and this represents the stereographic projection. So now comes the inverse pole figure and the pole figure. So pole figure is nothing but when the orientation is plotted relative to the sample's coordinate system. That is, you have the transverse direction here, RD, and if I ask you to, if someone asks to plot 100, it can be plotted, because all you have to do is, basically all it is doing is, it takes the grain, keeps at the center of the sphere, okay, having RDTD as the axis, okay, the RDTD sample coordinate system, and then keep the unit cell at the center and plot its 100 pole on the 2D, which is which is according to the procedure I have told earlier. Okay, so you get a distribution. So you can see here, this is a basically 002 pole. So 002 pole is actually hexagonal. In a 4 axis come means it is in the hexagonal crystal system. So it is actually 002 plane in the hexagonal, basically along the C plane. So that you are asking it to plot. So you see here towards the center. Okay, you see very an orange color, whereas far from it, then you see green color, and so that means when it's orange, you okay, perpendicular to the board of the plane, okay, perpendicular to the plane of the board. Okay, that is it is normal to RD. So this 002 planes are on plane normal is perpendicular to the plane of the board. Okay, so that is this what is it, screen, whichever screen we are seeing that. And then inverse pole figure is the opposite of that. Opposite means here the orientations are plotted related to the crystal axis. Now my grain orientations are not anymore plotted with respect to the sample frame of reference, but they are plotted with respect to the crystal axis. Okay, so that is inverse pole figure map. So this much information is also required for understanding the data. So now it comes my data. So I'm sorry that the scale bar is micron. Actually, it is in nanometers. Some mismatch was there. That is why it is in micron. So this is the TM data. So now you see here the TM image. Okay, so this is nanometer. Please bear with me. It is shown as microns. So you can see that 5 nanometer twins, actually you can see here 5 nanometer twins. So that you see the inverse pole figure. And then you see here when I asked, and I looked at the literature carefully, and I observed that the common plane, that is the plane common to these two, the crystallographic plane common to these laths. You see some laths, no, parallel lath. So it is nothing but bar 111. So which is that plane here? It is actually that plane I asked it to plot for both the maroon color and the blue color. So when I was plotting, I observed that both are very close. That means this TM diffraction pattern and the PED data are consistent. That is the twin plane is confirmed. The twin plane is bar 111. It is confirmed. It was much earlier discovered by various researchers. Probably it's 1980 paper. But when we did in using PED also, this was confirmed. Anyway, that way this it is a very small work. Much people have advanced this with many other works. Okay, so I thank the audience for their patient hearing, especially, and I thank Gumanath sir for giving me this opportunity for presenting this work. Thank you.
Thank you, sir. So, from the audience, if you have any doubt, you can ask now. And yeah, I think I can, if you have to, if you need any help from him in the future, I can share his contact details also. So if you need any type of help from characterization studies and all, I can share his details. Is it okay, sir?
Yes, sir. Actually, I am in metalworking lab. We will be happy to help also. Optical CM EBSD we have recently installed. It is getting installed. So definitely you can contact us. And if for TM diffractions, any information or XRD free softwares, I can suggest. No problem, sir. Anytime, sir.
Sure. Sure. Actually, I have one doubt. It was regarding my PhD. Sir,
Yes, sir.
I have some 3D printed samples. The surface is not polished. It has a lot
Okay,
of
sir.
micropores. So, whether we can do EBSD if the surface is not polished?
Yes, sir. Actually, the thing is, what scale is the pores? That is a question. Suppose you reduce the pores are, let's say, how much millimeter they are close. You can always do EBSD. Only thing is that you have to do an electropolishing to reduce the strain on the matrix.
Okay.
So because all this, I think you are working on some titanium or aluminum, no sir? Or,
Yeah, titanium.
sir, that can be. Only thing is that you have to get it a strain-free region. And porosity, definitely it will affect. But the thing is that what extent the porosity. Suppose it is you are interested to see from few 1 or 2 mm or less than that, few microns or 100 micron, 20 mm, then pores will not come into picture, sir. I think so.
Actually, my idea or my aim was to find out whether the face has changed after sintering. So whether that can be determined.
Sir, first you start with X-ray, sir.
Okay.
Then go to EBST. So X-ray, if it is not able to detect,
Yeah.
you can go next step. You go with to SEM, sir.
Yeah.
And SEM, you go for both etched and secondary electron mode, as well as etched, unetched and BSE. There are 2 modes in SEM. I couldn't cover that. SEM, there is backscattered electron mode.
Okay.
So in backscattered electron mode, you get contrast if there is a difference in average atomic number.
Okay.
Suppose you are producing some phase, no sintering, you are expecting some change. So if it has a different atomic number when compared to matrix, then definitely it will show a contrast. So first you confirm it with SEM, sir.
Sure,
Then you go with the EBST, because EBST again, if you want to characterize that phase, they will ask information like what is the crystal structure, what is the expected this one lattice parameter atomic, because you have to generate CIF file. Without CIF file, you cannot index that. To my best of knowledge, because EBST is just a comparison. You feed it to the machine already. What are phases are there? Then it will try to match, sir. It will not fetch from unknown source. It will not.
Okay.
Sir, first you verify, you do SEM, sir. Then you confirm that is the phase. Then you go, sir.
Okay.
And before that, do a thorough literature, sir. Because sometimes we tend to ignore some papers which will have some information related to that phase. Whether in Google Scholar you do a thorough literature survey, it will definitely, it may not get the data, but it will definitely give some guidance.
Sure, sir.
We can discuss that sometime, no problem.
Okay. Thank you.
Yeah, thank you, sir.
So I think there are no more queries from the audience. Anyway, if there is any doubt, you can contact him. I will share the details. So on behalf of Sripati Institute of Management Technology, I would like to thank Dr. Manu S Mohan for delivering this session. And afternoon session, we'll meet at 2 o'clock. The session is handled by Dr. Mudhusmati Roy Chowdhury on green composites. So till then, it's good afternoon, and I thank Manu sir once again. Thank you.
Thank you, sir. Thank you, sir. Thank you, sir, for giving this opportunity. Thank you.
Okay, I'll share the feedback form. You can fill it and send it. Thank you. Not for you, sir, for the participants.
Thank you, sir.
Okay, thank you.
Okay, sir. Thank you, sir.